All right, get ready to dive into something pretty amazing today. Electromagnetic waves. We've got physics lessons and even some stuff on radio. Should be interesting, right?
Yeah, definitely. It's crazy how they're everywhere, but we hardly ever think about them. Invisible, but so important.
Okay, so we're talking waves, but not the ocean kind, obviously. Our sources say these electromagnetic waves are like these fields, electric and magnetic, that oscillate. Visualizing that is kind of tough, like two jump ropes wiggling together.
You're on the right track. They're disturbances, basically, in those fields, electric and magnetic, and yet they move at the speed of light. That's like 300,000 kilometers every second.
No wonder we use them to communicate. Speaking of which, we got to talk about the electromagnetic spectrum, right? It's like the whole spread, from radio waves to stuff like gamma rays.
Exactly. Just like, you've got your different categories. Each wave on the spectrum has got its own thing going on, how it acts, what we use it for.
Our sources, they're organizing the spectrum by wavelength. So, radio waves, those are the long ones. Then it's microwaves, infrared. Then the light we actually see, all the way to X-rays and gamma rays, those are tiny, right? What makes them act so different?
It's all about this link between wavelength, frequency, and energy. Longer wave, lower frequency, lower energy. Shorter wave, higher frequency, higher energy. And that energy difference, that's the key to how each wave messes with, interacts with matter.
So a radio wave, all stretched out, it's weaker than a gamma ray, which is super tiny.
Exactly. That's why we can use radio waves for our phones and stuff, but gamma rays, those are dangerous. Got to be careful with them.
Makes sense. So radio waves first. What makes them good for communication?
Think about it. They can go super far, right through walls, everything. That's how you can listen to your radio inside, no problem.
Oh, right. And our sources say they go in every direction at once. One tower can hit tons of receivers. Efficient.
Totally. And because they've got the lowest energy on that whole spectrum, radio waves are pretty safe to use everywhere compared to some of the stronger ones.
Okay, next up is microwaves. Ovens, obviously. But our sources mention communication and radar, too. Anything else?
Microwaves, they're more energetic, yeah.
Yeah.
And smaller, wavelength-wise, good for things that need more focus. So yeah, ovens, but also satellite stuff, sending signals into space.
Whoa, so my phone might be using microwaves right now. Wild. And I remember reading they heat food by, like, shaking up the water molecules. What's going on there?
It's pretty cool, actually. Microwaves, they vibrate at just the right frequency, makes the water molecules go nuts, basically, and that creates heat. Perfect example of how a wave, even though we can't see it, can change stuff physically.
That's such a cool example. Okay, what about infrared? Heat, right? Like those cameras that can see in the dark.
Bingo. Infrared waves. Everything gives them off, as long as it's not absolute zero, temperature-wise. Hotter the thing, more infrared it's spitting out. Those cameras, they pick up that infrared, make images based on heat. Crazy useful.
So if we had infrared vision, we'd basically be seeing heat, not light. That's wild. And remote controls use that too, right?
Yep. Good example of how common infrared is. But here's the cool part. On that spectrum, infrared is right next to visible light. And that's the only part we see with our own eyes.
Which brings us to rainbows. Red, that's the longest wavelength in visible light. Violet's the shortest. ROYGBIV, remember that.
Classic mnemonic. And what makes a thing a certain color is all about which wavelengths it's absorbing and which it's reflecting back. A red apple soaks up all the colors except red, bounces that back to our eyes.
So it's not really red, it's reflecting red. Huh, I like that. And they say white light is all the colors mixed together, right? Like how prisms work.
Right. A prism bends the light, but each wavelength gets bent a little differently, so they separate out. White light goes in, full rainbow comes out. Pretty cool demonstration.
It is. Okay, so we've done radio, microwaves, infrared, and visible light. Now we're getting to the short and powerful stuff. What's next?
Up next is ultraviolet, UV rays, right? Shorter than the light we see, and they pack a punch. Energy-wise, I mean.
UV rays, the sunburn culprits. But our sources also say we need them for vitamin D. How can something be good and bad?
It's all about how much you get. A little UV from the sun helps our bodies make vitamin D, good for our bones. But too much, and yeah, sunburn, aging, even skin cancer, not good.
So everything in moderation. Our sources mention other uses too, like black lights. Those make things glow. How's that work?
Some materials, they soak up UV light, then they spit it back out, but at a longer wavelength, so it becomes visible light. We call that fluorescence. Black lights emit UV. We can't see it. But then it hits something, boom, fluorescence. It glows.
Whoa, that is cool. They're like converting the light. Okay, what about X-rays? Even more powerful than UV, yeah.
Oh, yeah, for sure. X-rays can go right through us, well, our soft tissues at least. That's why doctors use them so much.
Right, dentist loves their x-rays. But how do we even discover something you can't see?
It's actually a pretty cool story. Back in 1895, this guy, Wilhelm Röntgen, he's messing around with these tubes, kind of like old school TVs used, and he notices this screen glowing, even though the tube was covered up.
So something was getting through that he couldn't see.
Exactly. He figures out there's this invisible radiation could go through stuff that blocks normal light, called it X-rays, X for unknown, because he had no idea what it was at first.
That is so cool. And then that one discovery changed medicine forever. X-rays are also in airport scanners, right? So from our teeth to keeping us safe, pretty big impact. What about gamma rays? Those are the strongest, yeah.
You got it. Gamma rays, top of the charts, most energy, shortest wavelengths, highest frequency. They come from crazy powerful stuff in space like exploding stars.
Intense. What do we even do with them here on Earth?
They can be dangerous for sure in big doses, but we've figured out how to use them for good too. Doctors use them to kill cancer cells, and they're so powerful they can sterilize medical equipment, even food sometimes.
So even the strongest waves have their uses. This is blowing my mind. This whole spectrum, radio to gamma, all around us, constantly.
It really is amazing. And it shows you how smart people are, figuring out how to use these things we can't even see to make our lives better and learn more about the universe.
Seriously. It's kind of mind-blowing, like all those waves just overlapping right here, right now, and we've got no idea.
Right. And it's not like they're in their own lanes or something. We're swimming in electromagnetic radiation constantly from everywhere.
So we've got radio from every station, microwaves bouncing between phones, our own bodies giving off infrared, like an invisible party.
Exactly. And it's only recently we even knew about this stuff, let alone could use it. Makes you wonder, what else are we missing?
Right. And speaking of using it, our sources mention things that sound like sci-fi, like using certain wavelengths for night vision.
Some pretty wild tech has come out of understanding this stuff. Those night vision goggles, they take light off an infrared, which our eyes can't see, and they boost it, basically.
So it's already there, but they're making it visible. That's nuts.
It is pretty cool. Or those thermometers, the touchless kind. They're using infrared sensors to read the heat coming off us. No touch needed.
Wow. Magic. A few decades ago, it really shows you this invisible world that's affecting us all the time.
Absolutely. We've talked about a few uses, but let's dig into one that totally relies on these waves.
Yeah.
Radio communication.
Radio waves. It's in the name. But
Okay.
how do we go from invisible wave to hearing music, talking to someone across the world, all that?
Okay, so first step, you got to turn the sound, or the data, whatever you're sending, into electrical signals. Then a transmitter turns those signals into radio waves, shoots them out from an antenna.
So the antenna is like the bridge from our gadgets to the radio wave world.
Exactly. Those waves, they travel at the speed of light, and then a receiver with its own antenna picks them up.
Okay, sent the signal out, but how's it not a jumbled mess? Like, I don't hear my neighbor's phone calls on the radio, thankfully.
That's where tuning comes in. Each radio station, they broadcast on a specific frequency, right? Your radio's got a tuner, picks out just that frequency, blocks the rest. So you hear what you want, whether it's music or news or whatever.
So it's like a million conversations at once, but the tuner's my filter.
Good way to think about it. Now, even once the receiver grabs the right signal, it's still a radio wave. Got to turn it back into electrical signals our devices get. Demodulation, that's what we call that.
Demodulation. Sounds complicated.
It's actually pretty clever. Remember, AM and FM radio stands for amplitude modulation, frequency modulation.
Yeah, vaguely. School's a little fuzzy now.
Right, so modulation's like hitching a ride for the information. You change the wave itself, either its amplitude, that's the strength, or its frequency, how many waves are happening per second. AM does the amplitude, FM does frequency.
So it's hiding the info in the shape of the wave.
Exactly. And the demodulator in your radio, it knows how to unpack that and take the sound or data back out.
That's so cool. And all that's happening just so I can listen to my favorite song. We take it for granted.
Right, but it shows you we've gotten really good at using these waves to communicate.
Crazy amounts of info just sipping around us. And speaking of info, we mentioned analog versus digital signals. Where do those fit in?
Good point. Because how we send info, that's changed a lot with the switch to digital. Analog signals, they're continuous, like a smooth wave. Digital, it's all zeros and ones, on or off.
Like a dimmer switch versus a regular light switch.
Perfect analogy. Both can be sent via radio waves, but digital's got advantages.
Like what?
Well, digital, it handles interference way better. Because it's just two states, on or off, even if the signal gets messed up a bit, easy to fix. It's like writing a message in, I don't know, permanent marker. Even if it smudges, you can still read it.
Makes sense. And our sources say digital is easier to store, to mess with, send around, all that.
Exactly. You can squish it down, encrypt it so it's secure, send it as data super fast.
Yeah.
That's why everything's digital now.
So clear phone calls, streaming movies, downloading huge files, all thanks to that switch.
Yep. Totally changed how radio communication works, more reliable, way more info, all that. It's pretty amazing.
From understanding these waves to, well, everything we do now, it's a huge jump. It really makes you appreciate the stuff we don't see, how it all works.
Totally. And it's not just communication, right? Our sources mentioned GPS. That's a good one. Using invisible ways to find your way around, that's pretty wild when you think about it.
Right. I use GPS all the time, but how does it even work? It's like my phone just magically knows where I am.
It seems like magic, but it's really clever engineering, using those radio waves and a little bit of math. See, GPS uses a bunch of satellites up in space. They're like super accurate clocks, and they're always sending out signals, their location, and the time, using radio waves.
Okay, so signals from space.
Yeah.
But how does that turn into directions to the coffee shop?
Here's the cool part. Your phone, it's got a GPS receiver, right? Picks up those signals from a few satellites at once. And because we know how fast radio waves travel, with the speed of light, it can figure out how long each signal took to get to your phone.
Wait, so by those tiny differences in time, it knows how far away each satellite is?
Bingo. Needs at least 3, usually more, to get a good fix. Imagine this. You know how far you are from 3 different points. You can draw a circle around each one, with that distance as the radius, where they all meet. That's you.
So it's like triangulating my position, but from space. That's crazy accurate. And GPS isn't just for getting around, right?
Oh, no way. It's used for tons of stuff.
Sure.
Surveying, mapping, tracking animals, even predicting earthquakes. Self-driving cars use it too.
All that from understanding waves. It's
It
mind-blowing.
really shows you the more we learn about the universe, the more connected it all seems. Who knows what else we'll be able to do with electromagnetic waves in the future?
This whole deep dive has been incredible. We started with what they are, then that whole spectrum, radio waves to gamma rays, and how it affects our lives in so many ways.
It's easy to forget, right? We can't see them, but they're essential to how we experience the world, even to life itself.
Like we've been living with this whole hidden world around us, and it sounds like there's still so much more to discover.
Absolutely. Every answer leads to more questions. That's what's so great about science. Who knows what incredible things we'll find out next about electromagnetic waves or anything else.
I can't wait. Thanks for joining me on this electrifying deep dive. And for our listeners, keep those questions coming and never stop exploring.